All right, guys. Last vodcast for Unit 6. I know this seems like there's a lot. Again, this is specifically for the honors class. So if you're in the CP class, you certainly watch this, probably learn some stuff, but you're not going to be tested on this material as the honors classes are. We're going to talk a little bit about a couple of things that are sort of like bonding, but not quite the same in the same category as the ionic and covalent bonding that we've already talked about. So, first of these is something called metallic bonding. And we said before that metals do a little something different when they're by themselves. And by themselves, I mean, we're not talking about ionic compounds, so it's not like, it's sodium fluoride, so I've got a metal in it. We're talking about it's just a metal. So I've got like a big block of iron, or I have a block of titanium, or maybe I have titanium and iron blended together, but they're not bonded, it's just a mixture, okay? That's where metallic bonding comes into play. So what is metallic bonding? Metallic bonding basically says that the electrons are delocalized. Now, what does delocalized mean? Delocalized means that they don't belong to an individual nucleus anymore. They belong to sort of the whole group of metal ions, okay? And so if you look at this diagram, this sort of explains it, but I've got metal cations, okay, that's the plus signs. Those are the nuclei. So if this was iron, I've got a bunch of iron nuclei here. And then in between those is what usually gets referred to as like a sea of electrons. Basically, we've got a bunch of nuclei, and they're kind of just floating around in this sea of electrons. Kind of like if you went to the ball pit at Chuck E. Cheese, and you like jumped in, okay? The balls move all around you, but you can also move throughout all of those balls as well. So you have freedom of movement, and these metal cations have freedom of movement within this, just in the same way that you would in the ball pit. If the ball pit was like a regular crystalline structure, like ionic compound, the balls would be locked into place, and you jump in and none of the balls would move and you get hurt. Or you jump in and maybe you break the bonds, but they would crack apart. That's not true for metals. There's a lot more give in metals. They can move around a lot more. So if I try to push this one down, I can push it down. It can slide down into this sea of electrons here. So this leads to some pretty unique properties for metals, and you need to copy these down. These are three terms that you're going to hear a lot about for metals, and they all have to do with the way that metals are bonded. That metallic bonding, that sea of electrons, leads into each of these. So real quick, three definitions are malleable. Malleable, or you'll hear it referred to as malleability, okay, which is the ability of it to be malleable, means that you can hammer metals or roll them out into thin sheets. So you can get aluminum foil, or you can forge a sword or an axe or something like that. If you heat it up a little bit, you can bang on it and it will cause the metal to shift and bend, but not to break. You could do the same thing with gold. Like if you took a gold ring, if I took my ring off, I could pound on it with a hammer and it would not break, it would just sort of bend down, and then I could bend it back into place if necessary. That's malleability. Metals can be bent, and it looks just like this diagram. If I hit the nuclei with a hammer, if I hit a metal with a hammer, it just slides out of place. If I did that to a salt crystal, if I took a big salt lick or a salt crystal and hit it with a hammer, it would just shatter, okay? There's no give in it at all in a crystalline structure, but in metal bonding there is. Ductility, okay, or ductile, means that I can draw them into wires. That's how we get copper wires, silver wires, gold wires, all these metal wires that we need for all of our electronics. And then also to do with electronics is that metals are conductive. They allow electrons to flow really easily. Now, how does that work? Well, because these electrons are free. Okay, they're not attached to a particular atom. These outer shell electrons in metals are free, and so they can move freely. So if you apply a current, it basically pushes the electrons along, and they can move pretty freely. Okay, they're not locked into a rigid space like they are in a crystalline structure, and they're not locked into a shared bond like they would be in a covalent structure. Okay, so that's metal bonding in a nutshell, pretty simple. Next thing we want to talk about are intermolecular forces. Now, what in the world does intermolecular forces mean? Okay, here's the way it works. Everything that we've talked about so far has been bonds between atoms. So an oxygen is bonded to a hydrogen, bonded to another hydrogen. Intermolecular forces work like this, okay? That I've got billions upon billions of water molecules in even a small sample of water. And so intermolecular forces means how do the molecules relate to each other? So like I've got water molecule A here and water molecule B here. How do they interact with each other? Okay? And we'll see this in a second, these molecules actually have some attraction for each other. And so the attraction that the molecules, separate molecules, not atoms bonded together, but separate molecules have for each other, that's what intermolecular forces are. And I like to think about it, I mean, if you think about the prefix, intermolecular, it works the same way as the word interstate. So like if you have an interstate highway, it goes between states. So like 75, I-75, that runs right through our town here, it goes from Florida, okay, down, I believe it starts somewhere around Tampa. Actually, I think it goes down below that to Fort Myers and stuff. But I-75 goes through Florida. It goes through Georgia, Tennessee, Kentucky, Ohio, up into Michigan. It goes through several states. It's interstate. It goes between many states. And intermolecular forces means it goes between many molecules. Okay, so the super important example of this, and the one that if you miss everything else, the one that you absolutely have to get is hydrogen bonding. Hydrogen bonding is the strongest of these. It's the most important. It's the one that happens all the time. It's the one that is the reason water acts the way it does. It's the reason why DNA is curled up the way it is, why a lot of proteins get folded into the structures that they have to be to do all that lock and key enzyme stuff that you talked about in biology, all due to hydrogen bonding. So here's the way hydrogen bonding works. You have a hydrogen, that would kind of stand to reason, kind of silly to call it hydrogen bonding if you didn't have a hydrogen, okay, bonded to a highly electronegative atom. So oxygen is very electronegative. It's right next to fluorine on the table. So basically fluorine, oxygen, chlorine, a couple more things, usually those are highly electronegative atoms. So when that happens, you get this partial charges that we talked about before. You get this polarity, okay? I get a slight negative on the oxygen, slight positive on the hydrogen. And what happens is when we put a bunch of them together is that the negative on the oxygen on this water is attracted to the positive hydrogen on another molecule. And this kind of goes on and on. So like if I drew more water molecules here, okay, I would have more hydrogen bonding. Okay, oxygens on each water are going to get attached to hydrogens on other molecules. Okay? And this happens all throughout the water. It links them all together. Now, it is not the same as a regular bond. It's not nearly as strong as a bond between a hydrogen and an oxygen. So these are regular covalent bonds. Hydrogen bonds are usually represented by dashes or by these little lines like this. They're not full bonds, but they are pretty strong and they're super important. This is what makes water have surface tension. It's what gives it a high specific heat. It's why ice, solid water, has a higher density or a lower density than liquid water, which is really strange. This tight hydrogen bonding in water is what leads to almost all of water's really peculiar properties. So if you got to know one intermolecular force, you got to know hydrogen bonding. Okay, that one's super vital, massively important. Okay. Second one is basically the same sort of deal as hydrogen bonding, but it doesn't have to involve hydrogen. It's sort of a more generic term, and that is dipole interactions. What's a dipole? A dipole is just a molecule that has on one end a negative charge and on another end a positive charge. Okay? So like, how in the world would that work? Well, if I had a molecule that looked like this, okay, the fluorines are really electronegative, so they're going to pull the charge down to them, so that's going to give a little bit of a positive here, a little bit of negative on this end, so I've got a dipole, okay, positive on this end, negative on this end, okay. I don't even think that's a real molecule, but that's the general idea of how that would work. Now, when that happens, they're going to line themselves up, positive to negative end, just like hydrogen bonding. So, I mean, in principle, the way it works is the same as hydrogen bonding, but they're going to be weaker. Hydrogen bond is sort of a special case because hydrogen has such a low electronegativity, and then you take a high electronegativity and makes the difference really strong, which makes the poles stronger. I mean, if you think about them like magnets, in hydrogen bonding, these magnets would be much stronger than in a typical dipole interaction. Okay, so pretty simple. The last one that we're really going to worry about is something called London dispersion forces. Everything, the ones that we talked about so far, hydrogen bonding and dipole interactions, are for polar covalent molecules. Okay, kind of stands to reason. I mean, if we say dipole, okay, that means it has a pole. That means it's going to be polar. It has two different ends to it. Dispersion forces, though, work for nonpolar molecules, and they're really the only, usually the only force of attraction between nonpolar molecules. They're caused by the motion of electrons, and I'll show you this in just a second. But what that means is that the more electrons there are, the more chances of having dispersion forces. So if you have a bigger molecule that has a lot more electrons, then it is typically going to have bigger dispersion forces. So really small nonpolar molecules don't hold together very much at all, but the bigger they get, the more they hold together. And so real briefly, the way that London forces work is that, so here's what a nucleus looks like, right? You've got a nucleus, you've got electrons all around it, okay, and they're sort of whirring around, okay, buzzing around the nucleus. Well, as they're spinning around the nucleus, they're not like evenly spaced. They're kind of moving, a little bit randomly. And so inevitably what happens occasionally is that they all end up on one side of the nucleus, okay? Like these three are all over here on this side. Well, if they're all on one side, then that side has a negative charge, and that side gets a slight positive charge. Again, really slight negative, really slight positive. And that is going to allow it to kind of act like a dipole. Okay, now I've got a positive here and a negative here, and so the molecules can click up next to each other as dipoles. Now, the difference here is that these molecules are still moving, or these electrons are still moving, so they're going to move around. So that dipole that is formed is temporary. It's a very temporary dipole, and so it's going to go away. And that's what makes London forces the weakest of all of the intermolecular attractions, okay? Because they're not permanent, okay? It's there for a little bit, and then it moves away again, okay? So that's intermolecular forces and metallic bonding. Just a couple of more arrows in your quiver that you'll need to talk about bonding and how molecules relate together and how atoms relate together. So hopefully that wasn't too much more, guys. I know that we've got a lot of stuff in Unit 9. You guys have a total of 9 vodcasts altogether. But these are kind of simple things, and if you know the definitions and sort of look through the videos and see how these work, I don't think you'll have too much of a problem with these guys. All right? Thanks.